All right, so welcome everyone. My name is Olivier Roy, and I'm going to give you the tutorial on deontic logic for multi-agent system. So what is deontic logic? What is it about? Well, as I said in the abstract that some of you might have read, it's about normative notions like obligations and permissions. And I want to start by sort of motivating you why is it interesting from a multi-agent perspective to think about these notions. Well, let's start with obligations. So it seems like more and more we are automating a lot of the decisions we made or a lot of actions we take. So for example, we have automated auction. So programs or agents that bid for us. Some of you might have used snipers on eBay, right? Okay, this is something that takes action for you, right? Or there's big hype about Google cars, right? Automated cars that drive for you. I've just read before coming that in Germany they have designated the first stretch of highway that's going to be used to test these automated cars, right? Now the question is whether German drivers are going to let themselves be driven by things, given how important is driving cars in Germany. But so we delegate driving sometimes to computer, or we will probably in the near future, or you think about the use of drones, say in the military, for instance. Well, these are all cases where what we delegate to these computer agents are more and more morally complex notion, right? You incur more and more important responsibilities by carrying these actions, right? Bidding, right? You're responsible for the loss, or you being committed to pay, right? Driving cars, accident happened, right? Who's responsible? And of course, there's a lot of ethical questions that are raised by the use of drones and automated agents in warfare. So this is definitely an area where notions of obligations and permissions and ethical notions in general are of high importance, and they become more and more important for multi-agent system. But it's not always about like morality or the law. It can be much also about social norms, right? Some more mundane norms. So what are social norms? They are way of behaving, rules of conduct, which are in practice in a given groups, but could be otherwise, okay? Typical example, fashion, driving habits, right? If you're somebody from Europe, you arrive to India, you realize that the driving habits are a bit different here, okay? It's always, I can tell you, this is my third time in India now, it's always very impressive, right, when you arrive here, okay? So driving habits are a type of social norms that tell you how to do certain things, right? And if you deviate from them and you're the only one deviating, then you can incur some bad consequence, right? If I, as an European, start driving in India, but I don't blow my horn, I might get into trouble, okay? And the same here applied. These questions of social norms are also important for multi-agent system, right? You can think about, well, many of you have probably done some programming. There's some rule of programming, some rule of conduct, right? Rights of documentation on your code and so on, right? This is important. But there's also sometimes we program or we implement these social norms. For instance, in these P2P protocols, right? We implement something like sharing ratio because we think this is how it should be, right? Okay? So social norms are important. And this is all, so there's the law, there's these social norms, and there's also permission, right? And here I think as if you're from multi-agent system, I don't have to tell you that permissions are very important, right? You wonder what a certain program is allowed to do, which file is the program allowed to access, right? Or what happens if a program is accessing a file, the file is locked, is not accessible to another program, right? So this is a little cartoon. The slides are online, so I see a lot of people frowning, trying to read it, right? It's a XSCF, you probably know this website, very funny. It's a cartoon about sudo, if you're a Linux user, right? Sometimes if you try to sudo a command, and you happen not to be in a pseudo file list, you get a message that this incident will be reported, right? Well, this is important for us because it tells us that not only it's not possible for you to do it, but it's not even desirable to try, right? So this is not wished that you try this sort of access certain file that you are not supposed to. So again, we are in the realm of what you ought to do, but also what you're allowed to do. And we want to reason about these things. So this is what a tutorial is going to be about. Formal mathematical tools to reason about obligation, permissions, and related notion. So one thing I should say before we go to the plan or the more mathematical stuff. So Hans said it, but I'll say it again. Please ask questions during the presentation if you don't understand things or if you want to learn more. It's not only allowed, I would say it's obligatory, right? Okay. It's impossible that I'm totally clear on everything, right? So if I'm not clear, please ask questions. This is very important. And I should also say, you'll see I'm a philosopher by training, so I'm motivated by a lot of the conceptual notions that arise when you start thinking about obligations and permission. But I was pleased this morning to realize I was reading about what I think is the founder of the Institute, I think, which seemed to be a mathematical physicist, is what I understood, right? And it made me realize that the Institute of Mathematical Science is probably also not only about mathematics, but also use of mathematics in some science. Well, I'm a philosopher. I consider philosophy as a science. I definitely use a lot of mathematics in doing philosophy, so I think this is very fitting, and I'm very happy to be here. Okay, so what's the plan for the tutorial? Today, the talk is going to have two parts. I'll start by presenting you the essential of what is called standard deontic logic. It's a kind of model logic, very akin to the one that Hans presented in the previous tutorial, except we give it a different interpretation. Okay, so that's what I presented in the first part. Some historical background and, well, some what might people call limitation, but this is a debate that has been, we've moved past that by now, but I want to present you some limitation of the system. And then I will move to three current issues in deontic logic, things that people in multi-inch system, in philosophy, and in computer science in general who are interested in deontic logic are thinking about nowadays. Namely, a phenomenon that's called free choice permission. You probably don't know what it is. I'll tell you in the second part today. Then questions related to conditional obligation. So an example of a conditional obligation. If I make a promise, I should do what I promise. Okay, that's a conditional obligation, right? So if I haven't promised, I'm not obliged to do what I promise. Right? But conditional obligation turns out to be subtle and tricky, and there's a lot of interesting questions raised about them. And at the same time, we'll talk about normative conflicts, right? So these are situations in which it seems you ought to do two things that you cannot do at the same time, right? Suppose I promise Ram to have dinner with him tonight, and I also promise, I don't know, somebody else, and they're a completely different town, to have dinner with that other person. It seems like I ought to keep my promise to Ram, and I ought to keep my promise to that other person, but I cannot do both at the same time, right? Well, what should I do then? Right? That's a normative conflict, okay? And for the deontic logician, that's a very interesting question, how to resolve or to design logic which are sort of tolerant to these kind of conflict. And finally, I'll talk about some more recent work that I did with some colleagues in Munich about justification of norms. So we just not only want to know which norms follow from what am I obliged to if I'm obliged to something else, but also we want to know how do we justify these norms, right? And we'll see that by some use of modern logic machinery, we can tell a nice story about how this works. So that's going to be the last part. So again, 4 parts. I hope I can make it through the first 2 today, and then tomorrow we'll do part 3 and part 4. Okay? Again, if you have questions, please ask them along the way. All right, so essentials, that's the first part for now. What I will be drawing from substantially is actually a chapter, or many chapters, I'll give you reference along the way, from a recent book that Dov Gabay and associates have come out, or I've edited, came out last year, which is the Handbook of the Deontic and Normative System. I highly recommend it to you. It's a college publication book, so it's sort of relatively affordable. And this part I will draw from the first chapter of the book by Ilpidin and McNamara, where they give an excellent introduction to deontic logic, but also put it in its historical context. I will try to do a little bit of this today, but I will only be very sketchy on the history of deontic logic. And if you're interested in more of that, please have a look at this handbook article. Okay, so let's get started. So as I said, the language we'll be looking at is a modal language, a propositional modal language. Okay, so what we have in this language, we have a propositional part that's here, right? Okay, which contain the Boolean operator that we all know and love. So we have P, Q's, and R for propositions like "it is raining," "I promise to go to dinner with Ram," and so on. We have negation, and we have conjunction, and of course from that we can define all the other connective, right? So if you remember right, implication phi implies psi, right? It's just a shorthand in this logic for it is not the case that phi and not psi, right? Okay. Phi or psi. Just to warm up, what is it defined as? Yeah, so it is not the case that not phi and not psi, right? Okay, that's disjunction, right? And of course, once you have disjunction, you can give an alternative definition of implication, which we will use very often later on, namely, implication can also be defined as not phi or psi. Okay? Good? So that's just the basics, right? So there's something keep in mind, especially about implication, because we're going to use a lot of it and a lot of these various definitions as we go along. So that's the propositional part. We all know about it. Now, the deontic part is going to be this modal operator, the O that's there, right? Which we're going to interpret as it ought to be the case that phi. Okay? Now, this language allows you to put any formula in the scope of an ought operator, right? So you can define things like, you can write things like P ought to be the case, P and not Q ought to be the case, and so on. But you're also allowed to iterate obligation, right? And that's a question you might be interested in. What does it mean, right? You can say, it ought to be that it ought to be that P, for example. That's a well-formed formula, okay? Right. I will not talk much about iteration of the deontic modality here, right? Only mention in passing that whether iterated modalities, the deontic modalities are equivalent to not iterated one will depend on some assumption that you will make on the sort of semantics or the model that you will use. Okay? Right? But this is all the kind of formula that you're allowed to write down in this system. So, a couple of things already at the level of syntax that are interesting or important to keep in mind. Permission first, right? I said we're going to talk about obligation and permission. Well, permission is the dual of obligation in this framework. So, like we had this K hat in the talk before, which was the dual of knowledge. Now, permission here is the dual of obligation. So, we're going to define phi is permitted as it is not the case that phi is forbidden, right? That not phi is obligatory. Okay, so that's going to be the definition of our obligation, right? So officially, there is no P in the language, right? When I write it, but I will write a P for permission very often, but just take it as a shorthand for not, oh, not, right? Okay, so that's how it works. So that's permission. Now, something we can also say that's interesting is that we're going to come back to this in the third part, actually, is that already at the syntactic level, we can make a distinction between two types of conditional obligation, which philosophers have called wide scope and narrow scope obligation, right? So if I say that if I made a promise, I should keep it, right? I could interpret this as saying, well, if I make a promise, then it ought to be the case that I keep it, right? But I can also interpret that as it ought to be the case that if I make a promise, I keep it, okay? Well, the first one here is what's called a narrow scope conditional obligation, and the second one is called a wide scope, okay? And this can make a big difference, right? So think about requirements on belief, right, okay? One thing what people think it's a plausible requirement is if I believe it's raining outside, I should not believe that it's not raining outside, okay, right? Let's agree on that, right? All right, okay. Now suppose, yeah?
How is not permission stated in terms of obligation? If you're not permitting something?
Yeah. So not P phi? Yeah, right. Well, you can use this definition, right? So you unpack this. So this is the same as saying it is not the case that you ought not phi, right? Okay. But of course, double negation, this is a classical negation, right? It disappears, right? If something is not permitted, then it's just forbidden, right? Very good, very good. Okay.
What do you say by wide and narrow scope? I mean, this entire formula is...
What's the difference?
No. I understand the difference, but what is the definition of wide scope, or what is the definition of narrow scope?
Right. So a narrow scope conditional obligation is an obligation of that form, and a wide scope is an obligation of that form, where the implication as a whole is within the scope of a deontic operator, right? And so why would we want to make this distinction, right? So, okay, if I believe that it's raining, I should not believe that it's not raining. Okay, we agree on that, right? Beliefs should be consistent. At least they should be, right? I'm not saying they are, but that they should be, right? Okay. So suppose I believe it's raining now. Okay. Scope obligation, right? Then I ought not to believe that it's not raining, right? Okay.
But in that case also you don't need any kind of relationship between P and Q. I mean,
No, right. That's right. In this case, they are, right, with belief and not believing, but it need not to be, right? That's perfectly right. So, but suppose, I'm in a case where I'm believing it's just raining. But suppose now that my belief is completely came out of the blue, right? I'm totally unjustified of having my belief, right? Actually, all my evidence point into the fact that it's not raining, right? So what I ought to believe actually is that it's not raining, right? Okay, so what I should do is actually drop this crazy belief that I had in the first place, right? So the narrow scope here gives us the wrong answer, right? It seems like in this case, what I should do is either form the belief, avoid the belief that it's not raining, or drop my belief that it is raining, right? And this is precisely what the wide scope is giving you, okay? So in some cases, right, you want to prefer the wide scope over the narrow scope. But sometimes, actually, the narrow scope does the better answer. So if you think about cases where you think about rationality as meeting your own standard, right? So if I think I ought to help my neighbor, then I should help my neighbor, right? Okay, so if there's a norm that I accept myself, then I should follow that norm, right? Okay. Now, if I have a narrow scope reading of that, right, what do we get is that in case where I ought, in fact, not to help my neighbor, right, then what I should do is drop my belief, but maybe my belief is perfectly justified, right? So if my belief is justified but it's mistaken, right, could be justified but still mistaken, right, then it seems that indeed rationality as meeting your own standards say that you should actually do it, right, even though in fact that's not the case that you ought to do it. Okay. So this is a discussion that's been going on in philosophy for a long time. It is still very active, but here already standard deontic logic gives you a nice distinction between these two notions, right? Yeah.
In all the examples,
Yeah.
Whereas now we're talking about
Yeah.
things with truth values. I mean,
With belief.
yeah, so this is professional obligation.
Very good.
Obligation with action.
Yeah. Thanks for mentioning that, right? So it's a classical distinction in deontic logic, right? That you can have two kinds of obligation. You can have ought to do obligation, and you can have ought to be obligation, right? I can say, I ought to help my neighbor, that's an ought to do, but I can also say, the world ought to be a better place, right? That's an ought to be obligation, right? Well, this, yeah.
Relate to disjunction. What I mean is, you ought to help your neighbor,
Yeah.
and ought to help your neighbor, ought to kill him.
Yeah. Very good. So we're going to talk about precisely that sort of introduction of disjunction towards the end. That's one of the so-called paradox of deontic logic, right? So we'll do that, right? But so on the ought to do, ought to be distinction, so this logic can be seen, at least at the outset, as a logic for ought to be, because we talk about ought operator applying to what Hans called facts before, right? PQs are, it is raining, I promise something, right? Okay. But of course, there are some analysis on the market that try to capture ought to do in terms of ought to be, right? So if I ought to help my neighbor, it means that it ought to be the case that I perform the action of helping my neighbor, right? Now, this analysis doesn't go all the way philosophically. There's some problem with it, but at least it gets you far enough that we'll keep it from now, right? So if you want to think about ought to be, that's one way to think about it. But if you know a little bit about modal logic, you know it has a natural translation into first-order logic, and you can think of your object or your domain as action token and the proposition as describing action types, and here you have a logic of ought to be, ought to do right away. Right. Okay. So it's possible, but of course it requires a bit of a mind twist from what you're used to do from these P's and these Q's. Okay. So that's enough for syntax. Now I'm going to tell you how we are going to interpret this logic, and we're going to do it in essentially the same way as Hans interpreted the deontic, the epistemic operators in the previous talk, namely using something that's called Kripke structure, right, or possible world semantic, or here, because it's deontic logic, we're going to call them deontic frame. So a deontic frame, very generally, is a pair of a set of possible worlds or possible state of affair or complete description of what's relevant to the situation you want to analyze, right? And a relationship, a binary relation between these state of affairs, right, that tells you which states are normatively ideal compared to other ones. Okay, so let's take a very simple example. Right? Okay, let's say I have the following models, the following frame. I have W1, W2, W3. Right? So when I draw an arrow, it means that the relation goes from W1 to W2, but not the other way around. Right? If I draw a double arrow, then it's symmetric, but in this case it's not. It need not necessarily. Well, you can think this arrow goes both ways, and maybe there's a reflexive arrow on both these states. So how to interpret a simple model like this? Well, from the perspective of W1, both W2 and W3 are ideal. Right? This is an ideal situation where, say, no norm is broken, everything is as it should be, and so on and so forth, right? There's no violation of security or whichever way you want to think about ideal state, right? Okay? There's no poverty in the world. Okay, whatever you might want to think, right? And from the perspective of these two worlds, right, from W2, W3 is normatively ideal, but also vice versa, and W2 is normatively ideal to itself, right? So things are as they should be in W2. Okay? Right. But that's a very simple model, right? But that's the kind of model we will use. Of course, deontic frames can be, so I said models, I'm sorry. We're going to move to models in a second, but now they are frames. So deontic frames can be very complex, right? Your set of state can be infinite, right? Can be very big, right? The relation can be very complicated. But this is essentially what they are. A collection of possible worlds and a relation, a binary relation between these worlds. And the difference is that we interpret this relation as normatively ideal. Yeah? No, not necessarily, right? Very good. It means that, so I will tell you about property of this relation in a second, right? So in Hans' talk, we assume the relation to be reflexive, right? So every world is accessible to itself. Now, we don't want to assume that here, because if you think intuitively, from a perspective of a given situation, it need not to be the case that the current situation is ideal, right? Maybe we can move, we have to move somewhere else to move to an ideal place, right? So if there's poverty right now in the current situation, then this is not ideal, right? So if we want to move to any ideal situation, we have to move to another world. So then there will be no reflexive loop, right? So the relation will not necessarily be reflexive. That's perfect. That's correct, right? Okay. And here we are. Properties of the relation, right?
So that's my class. What is, can you have W1 arrow, W2 arrow, W3?
Yes, you can, right? So this idea of relation gives you a very contextual notion of ideal, right? So what's ideal depends on the world you start from. So if you have a case where, so you were considering a case where you have W1, W2, W3, right? Well, it's a case where W2 is ideal from the perspective of W1, but once you've reached W2, it's not good enough. You have to move again, right?
Make your first million.
Right, exactly. Make your first million and then keep going, right? Okay, that's the way. Okay, yeah.
So it's not possible to have a world which doesn't have an outgoing.
Ah, very good. So what the condition you're talking about is the condition what's called seriality here, right? Okay, it says, so a deontic frame is serial when for every world there is an arrow going out of it, right? There is no blind world in modal logician jargon, okay, right? So this is a condition you might want, and actually this is a condition that we will assume here, right? So it's never the case that you end up in a blind world, and we will see the consequences of that later on. But these are a number of other assumptions you can make. You can assume that the relation is transitive, right? So if you can move like this from W1 to W2, W2 to W3, but if the relation is transitive, then you can also make a move like this, right? Okay, from W1 to W3 directly, okay? But I will not assume transitivity at the outset, okay? The relation could be reflexive, that's what we just talked about, right? Every world can see itself, but we do not want to assume that, right? Okay? Or symmetric, right? So if you make a move from W1 to W2, then you can go back, right? But indeed, this need not be the case, right? And I guess this example tells you a reason why, right? If I have to move to a world where there's no poverty to move to an ideal world, well, of course, there's no reason why I should move back to a world with poverty once I've reached that state, right? Okay. So indeed, the only condition that we will keep in defining a deontic frame is seriality, right? We assume that for every state, there is an accessible one, right? There's no blind state, okay? There's always an outgoing arrow from each world, okay, right? So it's sort of an optimistic view, right? From every state, there's an ideal state you can reach from here, right? You ever end up in a moral deadlock or something like that, right? Okay? So that's the idea of seriality. Okay. Now, a model is just a frame, in the same sense that Hans talked about, is a frame in which you add a valuation which tells you which propositions are true at each state, right? So formally, a valuation is a function from your set of state to subset of a given set of propositional letters, P, Q, and R, right? Okay? So it tells you at each state which proposition are true. So if you want to turn, for example, this frame into a model, right, you can say, for example, P is true here, maybe it's false in both of them, right? And Q is true here, maybe, and Q is false here. Okay, right? So I write not P dot Q just to make it clear, right? But normally, technically speaking, if something is false, if a proposition is false at a state, it's just not in the valuation at that state, right? Okay, so, but we'll see the semantics makes these two things equivalent. But that's what a model looks like. It's just a frame decorated with some propositions that are true at this state. It is just for atomic propositions, okay? Good. So now that we have that, we can define what it means for a formula to be true in the deontic model. And this is, again, the standard modal logic definition of truth in the deontic model. So an atomic proposition P is true in a model at a given state if and only if P is in the list that the valuation gives you at that state, right? Okay, so P is true at W1, for instance. Okay. Now, conjunction and negation, as you know them for propositional logic. So a conjunction is true if both conjuncts are true at this state. Negation is true if the negated formula is not true at that state. Of course, what we're interested in is the modal clause, the clause for obligation. So O phi is true if and only if phi is true in all the accessible state, all the normatively ideal state from W. Okay? Right. So again, let's go back, right? Okay. So is P obligatory at W1? Well, no, right? It's not. Actually, it's forbidden, right? Why is that? Because in all the ideal state, P is false, right? Very good. Now, is Q obligatory? No, right? Why is that? Because there is an ideal state in which Q is false. But then is Q forbidden? Neither, right? Because there's an ideal state where Q is true, right? Okay? Right. So this is how the truth condition for the O work. So you look at all the accessible state, and you check whether the formula you're interested in is true in all of them. And for O phi to be true, it has to be the case that all of them make phi true. All right? Good. So that's definition of obligation. Now, you remember I defined permitted phi as not O, not phi, right? Okay. So what will be then the truth condition under which condition P phi is going to be true? What? So I define P phi as it is not O, not phi, right? So not phi is not forbidden. Not phi is not forbidden. So then under which condition is phi permitted in that model? Q? Yeah, so P phi, right? So when is phi permitted? Yes, right? There is a word, right? So you take this definition, right? You negate the existence, the for all quantifier, and you push the negation inside, right? And you get phi is permitted if there is an ideal state in which phi is true, right? So the thing to keep in mind, right, is that O is a universal quantifier and P behaves like an existential quantifier. Okay, that's the analogy we should keep in mind all the time, at least in this framework. And again, just to connect to what Hans was saying, this is essentially the same truth definition as Hans gave for K, and this was for K hat, right? Okay, so that's essentially the same, except the frame conditions are different, right? Hans was working with equivalence relation, we are not. Okay? Good, so now we're gonna go through a number of standard notion, right? So a formula phi is valid in a model if it's true everywhere, right? Okay, so if I look at every possible world in that model, phi is true, then I say phi is valid. Okay, right? Phi is valid on a frame if it's valid on all model based on that frame, right? So this you might, I went quick on that, right? But just to remind you, a frame, a model is a frame plus evaluation. So if I have a given frame, there's tons of model that I can create by putting them different valuation, right? Make P true at different states, right? Okay. So for a formula to be valid on a frame, it has to be valid whatever valuation I can put on it. Okay? Now, if I have a particular class of frames, for instance, the class of transitive frame, I can wonder what it means for a formula to be valid on that class. And this is going to be precisely what you expect, namely, a formula is valid on a class of frame if it's valid on all the frame of that class, right? And a little convention, I'm going to use double turnstile file with nothing before it, just to say that it's valid on the class of all deontic frames. Okay? Now remember, I make only one assumption on the deontic frame, namely that the frame is serial, right? So there's always at least one outgoing arrow, right? Okay. Good, and now we can see a consequence of that, right? Okay. So because the frame is serial, the following principle become valid, which is very intuitive. If something is obligatory, then that thing is permitted. So if I ought to help my neighbor, then it's permitted to help my neighbor. Okay. Now, why is this valid? Well, to show that, we have to show that on any deontic frame whatsoever, if I take any model for that frame, this is going to be true, right? Okay. So take an arbitrary world. Oops. Let's erase this. In an arbitrary model with an arbitrary valuation, so I don't know much about this thing, right? Okay. Except assume that phi is obligatory there, right? If we can show that phi is permitted, then we're fine. Well, you can see how this is going to go, right? I know because the frame is serial that there is at least one accessible world, call it V, from that state, right? That's just a consequence of seriality. Because phi is obligatory, right? I know that phi will be true in all the accessible states. So in particular, this will be true in this one. But then I found my accessible state where phi is true. And you remember, you just observe, p phi is true if and only if there is one accessible state, which makes phi true, right? So that's enough to make p phi true here, right? Okay? So simple as that, right? Seriality gives you O phi implies P phi. Actually, yeah?
Just we wanted this one, that's why seriality relation was taken or some other motivation?
What?
We wanted this property to have.
Yeah.
That's why seriality relation is taken?
Good. Good question. So there's two ways to think about it. You can think of it in terms of the formula. You can think this is a very plausible formula, right? And it turns out that this formula corresponds to the frame being serial in the following sense. A frame is serial if and only if it validates that formula. Okay, so if you like that formula and you add it, then you work by that very fact into the class of serial frame. But you can also start from the frames, like we discussed earlier, and think if my relation is a relation of being normatively ideal, right, then it makes sense to think that, well, if you're positive at least, right, that there is at least always at least one ideal state from the current one. And then you get that. Okay?
There is some kind of state similarity with the notion of existential import or
yes. Yes, definitely. I mean, what this
for all
exactly, right? So you can view this thing as saying, if for all phi, for all accessible state phi is the case, then there exists one, right? Okay? But seriality tells you that there's always one, right? So you can do that sort of existential import. Okay? But that's because the frame is serial, right? That's very important, right? This is precisely what's happening. Good. So Hans talked about two ways to look at things, the semantic way and the syntactic way, right? Well, you can think of it as, so now we know what the valid formula is on the class of all deontic frames, right? It's a formula which whatever frame I take, whatever model I construct on that frame and whatever world I take in that model, the formula will turn out to be true, right? Now, you might want to ask, can I capture in a neat way this set of valid formula? And yes, you can. Actually, standard deontic logic is a well-known model logic. It's a logic called KD, okay? So it contains all instances of propositional tautology, right? So all your favorite propositional tautologies, right? So why are we doing this? Because we don't want to bother with axiomatizing propositional logic. We're interested in the model case, but of course you could do with something smaller. And then we add the following two axioms to that logic, right? All instances of the K axiom. We've encountered this morning, right? It was, in terms of knowledge, it was closure of knowledge under known implication, right? But here it's closed under obligatory obligation, right? Let's put it this way, right? So if phi implies psi is obligatory, then if O phi, then O psi, okay? And the second axiom is essentially O implies P that we just seen, which characterize seriality. So you add all the instances of these, and you close under these two rules. Modus ponens, which we know. So if I have a proof that P implies Q, that phi implies psi, and I have a proof of phi, then I have a proof of psi, right? And the necessitation rule. So if phi is a theorem, then O phi is going to be a theorem as well. Now these rules are important. In the antecedent of the rule, it has to be theorems, right? Otherwise, so it's not like if I assume phi, I can get O phi, because otherwise it's very easy to prove phi implies O phi, and we don't want that, right? So if something is the case, it's not necessarily obligatory. Yeah?
Sounds a bit strange to say that 2 plus 2 plus 4 should be obligatory.
Very good, very good, okay? So now we're entering the rise and the fall of standard deontic logic, okay? So it's called standard deontic logic, not because everyone likes it, right? But because that's the point of reference, right, okay? But it has a lot of shortcoming or counterintuitive consequence. For example, it ought to be that, well, I mean, it makes mathematics very ideal, right? But it ought to be that 2 plus 2 equals 4, right? It sounds weird. You might think, especially if it's ought to do, right? You might think it has to be that there's a possibility to do otherwise, right? But that cannot be the case for tautologies. Well, it's something you don't get in standard deontic logic, right? Okay. So nowadays, standard deontic logic is the logic you situate yourself from, right? You say, my logic is different from SDL because of this and that, right? But it's not the one that says, great, I agree with standard deontic logic because there's many shortcoming or limitation of that. Yeah?
Instead of taking K, could you take a rule, obligatory phi or psi, obligatory phi, hence obligatory psi. So instead of taking the implication in psi,
yeah,
you take that and
yeah.
put that.
Well, so one thing you could do is indeed do some kind of disjunctive syllogism, right? You could say obligatory phi or psi, obligatory not phi, hence obligatory phi, right? This you could definitely do instead of K. Yeah.
But that perhaps is the same.
Yeah. Well, yeah, sure. Well, we can discuss it.
The point is that here also deduction theorem in general will not hold.
Well, it depends how you define that. So the deduction theorem for modal logic is a tricky question. It depends on how you define it, right?
That's why K
yeah.
is quite strong than just taking.
Right. So the deduction theorems would say something like that, right? And that's terrible, right? Okay? We don't want that, but it's looked like this is precisely what we have for necessitation, right? Well, of course, it depends on how you're going to define semantic or syntactic consequence relation, right? And if you do it in a local way, I didn't talk about this, but you can define a local consequence relation, say, for every state, this is the case, and that is the case, then of course, this doesn't hold either,
yeah,
right?
That's why my point is this, that you say in general deduction theorem doesn't hold.
Yeah.
If instead of K,
yeah.
you took a rule,
yeah.
Which will be more relaxed in this.
Yeah, okay.
And if that serves the purpose, this also, I mean, my question to Hans.
Good, okay. Two ways to answer to that. I'm one of those persons who think that actually who agree that the deduction theorem does hold. It's just a matter of how you define the consequence relation, and you have to be careful about it. Okay, but we can disagree. We can discuss that. Right? But one thing we will do, and we will see in the second part, is actually that you can define modal logic which are weaker than K, right, and which make do or get away from all the strong consequences of K, right, or many of them, right, without committing you to something like that. And we'll see some of these. Okay, good. So just to flash a result, this standard deontic logic is sound and complete with respect to the class of deontic frames. What does that mean? It means that it captures precisely the set of formulas which are valid on the class of deontic frame. So if a formula is valid, then it's derivable using the syntactic rules in that system, and vice versa. If the formula is derivable, then it's valid on the class of all deontic frames. Okay? So syntax and semantic match precisely. Good. So a couple of things. I will not have time to prove them. You can try them at home if you want. Try them syntactically. This is much more fun, right? Okay. So one thing we will use very often in the following is that O distributes over conjunction. it's actually equivalent to conjunction of obligation. So if and this is a theorem of SDL. So if I ought to help the poor and keep my promise, right? Then I ought to help the poor and I ought to keep my promise. Okay? So these are two. This is a consequence. This is a theorem of SDL, right? And you can try to prove it. It follows from K and necessitation, right? Okay? That's an important theorem. And also an important rule that we will use, right, is if phi implies psi is a theorem, then I can conclude that O phi implies O psi, right? And this is sometimes called monotonicity, right? Okay. Now this rule is probably a bit more obvious to see, right? Because where does it come from? Because if this is a theorem, by necessity I can put an O in front of the whole negation, right? But then I can apply K to it and modus ponens to get the conclusion of the rule. Okay? Right? So this is an important rule, but it's a bit clearer. And actually you can generalize that, right, to cases where you have a complex conjunct, right? You can say O phi 1 and blah, 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 phi n implies psi, right? From that, I can put an O in front of all of these, and it's also true. Okay, right? Well, once you have this one and this one, I guess you can see where this is going to go. How this is going to go. Okay. Good, so these are things to keep in mind that are useful. Now, one important thing you get in this logic right away, right, is that this logic is conflict intolerant, right? It rules out normative conflict, okay? And that's an interesting thing because it comes from this principle that I hope you by now have accepted, namely that O phi implies P phi, right? Okay. Why is that? Well, remember, right? Implication is a shortcoming for it's not the case that O phi and not P phi, right? But then we had a question earlier, what does it mean for not P phi to be true, or what does it translate, right? Well, if I unpack not P phi, I guess I get this, right? Okay. But of course, double negation disappear again, right? So it's not the case that I ought to phi and I ought not to phi, right? So this logic just rules out from the outset normative conflicts, okay? And this follows, this is actually just a rewriting of O implies P. So that's something philosophically interesting, right? So we started with a theorem or a formula which thought we were plausible, and we found it has this much stronger consequence, namely that normative conflicts are ruled out. And we will see in the third part that indeed sometimes you do want to account for some normative conflicts, right? Maybe rationality tells me to be an egoist, but morality tells me to be an altruist, right? What should I do, right? I want a logic that tells me what should I do without exploding in logical jargon. Okay, and this we'll see in the third part. Now, quickly, a bit of history. So standard eidetic logic, or as we know it, has sort of evolved in the first half of the 20th century. Really, the first work that's credited to be sort of modern, the deontic logic, is the works of Ernst Mali, which was an Austrian philosopher and logician. But the logic was not very successful because one of his theorem was this. It was not an axiom, right? Mali was not as, he was not taking it as axiom, but it was realized very quickly that the logic was deriving a complete collapse of the modal notion. So O phi was just equivalent to phi, right? Which is not very desirable, right? I mean, neither direction, right? So if phi is obligatory, it doesn't mean that it's the case. And if phi is the case, it doesn't mean that it's obligatory, right? So you definitely don't want that, okay? But Mali's work has sort of generated a lot of discussion, and the official birth of deontic logic is usually credited to von Ritz, 51 paper in mine, where he proposed something which is not quite SDL, standard deontic logic, but very close, because von Ritz rejects necessitation. So he was precisely agreeing with some of you that it should not be a theorem of your logic that 2 + 2 = 4. Right, okay? But necessitation is just something you have to accept as soon as you give a Kripke style semantic that I gave you in terms of, that is, O-Phi in terms of truth in all accessible world. Okay. So von Rit was rejecting it, but there was no semantics, at least in the 51 paper of von Rit. It was just syntactic, just axioms, right? Okay. But from there, standard deontic logic sort of evolved. One important historical development, which I will not talk about, but I just want to tease your curiosity on that, is Alan Ross Anderson, which is here, and Stig Kanger, which is there, proposed at the end of the 50s something which is called, by now it's called Anderson-Kanger reduction, where they define the deontic operator, like ought to be, in terms of alethic model logic, what's necessary and what's possible, and some constant. This is bad, right? Okay, so a constant B, which says you're in a bad state, right? And basically, something is obligatory if you don't do it, you necessarily end up in a bad state, right? Okay, that's roughly the Anderson-Kanger reduction. Interesting work. The deontic logic you get has interesting property. It's close to SDL, but not quite. So just these pictures. So this is Mali, right? Looks very serious. This is von Rit. This is Anderson. This is Kanger. And this is nobody who's named here, but I thought this was a nice picture. And he also did a lot of deontic logic. That's Christer Segerberg when he was very young. So, yeah, that's Segerberg, right? Yeah. Okay. So, yeah. And Segerberg also did very interesting stuff on deontic logic. So he's not there only for the nice picture, right? Relevance logic. Yeah, that's the same. Yeah. Good. So that's a bit of history. Now I just wanted to so standard deontic logic has been applied in various, or deontic logic has been applied in various disciplines. And I just want to give you a bit of a sort of shopping list or things you can look for. So in law, there's a big field called law and AI. It's not all deontic logic, but some deontic logic is made there. So there's very early paper by the same, this is a typo, this should be Stig. Sorry, so this should not be there, right? STIG, this is what it should be. So the Stig Kanger and Helle Kanger who wrote a paper, Right in Parliamentarism, where they analyze the Hoffelian theory of rights. So it's a well-known theory of rights in legal theory, using deontic logic. And this sort of work is still very active nowadays. And actually, so for those of you who know belief revision theory, right, you know the AGM, right, Alturon, Makingson, Garenforth, Makingson, right? Well, the same Alturon actually started his early work, and he continued to do that, was actually on the logic of norm change, right? And that was his original motivation to look at systems of change. And so Alturon actually did a lot of interesting work on dynamics of norm using something that looks very much like standard deontic logic. And if you're interested in looking at what's been done nowadays on that, I can definitely refer you to another paper in the handbook by Surgot on what's called normative position, right? So Surgot, I've worked a lot on the intersection of legal theory and AI. And that's an excellent review paper on that. So this is a screenshot from the Logic and Law and AI conference, which has been running for a long time. Actually, it's coming again this year. This is Henry Prakken, which some of you might know, also a very active researcher in deontic logic and law. This is Giovanni Sartor, and this is Antonino Rotolo. Both of them also big actors nowadays in the intersection of deontic logic and legal theory. So this is a fruitful and very active field right now. And of course, deontic logic in computer science has a long history, right? So there's this book, which is by now relatively old, by Weichinger, and Meyer, which is a bit dated, but it's actually interesting to look at because they are all already at this point sketch interesting application of deontic logic. But there's a long-going conference theory called DEON, which I really suggest you to look at if you're interested in application of deontic logic in computer science, which publish every 2 years a proceeding of the conference where you can actually find what's happening in deontic logic right now by looking at the DEON proceedings, okay? So now they want to broaden their scope, so they recently changed their name. It's called Deontic Logic and Normative Systems now. but it was for a long time called deontic logic in computer science because its main base is indeed still in computer science. And there's the deontic.org website, and you can have a look. There's a lot of information about what's going on. Okay, and now two teasers. So deontic logic started in philosophy, right? But then it went like some of model logic went to computer science, but now it's making a big comeback, especially in the US. There's a lot of interesting work done on what philosophers call deontic models, but that's essentially deontic logic. And they're rediscovering some of the stuff that computer scientists and linguists have been doing. So key names here, Colodny, McFarlane, and Cariani. If you're interested in that, look for these names. In deontic logic, you'll find interesting stuff. And in linguistics, deontic logic has been developed and investigated because you can think of, there's a very close, actually, historically speaking, it's also been investigated in close relation with imperative, right? You can think of norms as being connected to me giving you an order, right? When I say you ought to help the poor, right? What I'm telling you is help the poor, okay, right? Of course, there's some dissimilarity, but there's a lot of analogy, and you can draw from that to analyze both deontic models and imperatives and performatives in general, right? When the lawgiver says, right now it's illegal to drive on the right in India, right? Well, it makes it illegal, right? So it's a performative check, right? So there's interesting linguistic phenomena related to that. So again, so deontic logic is very active in all these fields. I want to finish this part just by telling you something about the so-called deontic paradox. So if you look at the Stanford Encyclopedia entry on deontic logic, you have the impression that deontic logic is all about paradox, bad consequences of standard deontic logic. Here's one that we mentioned earlier. If it's permitted for me to send a letter, it's permitted for me to send a letter or burn it. Okay, that's a validity in standard deontic logic, which you might not like, and that's called the Ross paradox. Another one, if it ought to be the case that you help someone and that person is injured, then it ought to be the case that someone is injured, right? This one is a bit more contested, but nonetheless, just take it with the history of deontic logic that this is not a bad consequence, a good consequence, right? Okay. And there's Chisholm paradox, which is about going to parties. We'll talk about this actually in the third part, so tomorrow morning. But so all these paradoxes have spread or created a lot of research in deontic logic, trying to devise systems that avoid these paradoxes. Yeah?
First paradox, you have another statement saying that if you burn it, you can't send it. So without that, you get it is a paradox.
Well, right, okay, very good. So these are not paradoxes in the sense that you derive a contradiction from them. These are paradoxes in the sense that these are counterintuitive consequences of. So these are just perfectly consistent formulas in the language, right? In fact, they're theorems, right? Okay. So it's not that the logic is inconsistent, right? That's right. So it's, I guess, for rhetorical purposes, we call them paradoxes, right? But these are not things like the Russell paradox, which you show that the system is inconsistent. Very good. Yeah. So these are just bad consequences, things you do not want to be valid about obligation and permission. Now, let me tell you this way, we know by now thousands of ways to avoid these paradoxes, right? So devising a logic which avoids these paradoxes is something which is known, has been done thousands of times. And the practice of deontic logic nowadays is not anymore about devising systems that avoid the deontic paradox, right? And that's the way I want to present you deontic logic right now. So what I think is interesting is a number of different issues in avoiding the paradox, and this is what I'll present you now. The paradoxes have been important in triggering intuitions and make us think about the logic of norms. But by now, if your only worry is to avoid them, we know many ways. I think your problem is to choose which way you want to avoid them, right? As opposed to devise a way to avoid them. Okay? So deontic paradoxes are specific to SDL. We know many ways to avoid them. And the question is, well, what can we say otherwise, which is interesting about deontic logic? And this is what we'll do from now on. Okay, so the next part is going to be about that. Okay, so that's the end of the first part. I was planning to do a little break while I switch the slide, so it's going to be a 2 seconds break. So take a break right now. Okay, I hope you're having a nice break. Now the break is over. Okay, good. So in the interest of time, I'll just go on. Okay. So in the second part, I want to start focusing on issues which are currently investigated in deontic logic, which I think are interesting, and as you might have guessed what I just said before the break, are more interesting than avoiding the paradoxes. Yeah?
You didn't say much about multi-agents.
That's right, that's right.
Just one agent.
Yes, and the reason is that I guess all the issues that I've presented you, I think they are highly relevant actually for multi-agent system, right? But I will keep it at this philosophical level. So if you're interested in looking at more application in multi-agent system, I can definitely refer you to the early work of John Meyer, which I quoted earlier. There's a lot, an interesting application, right? And the sort of logic that I will present in the third part actually comes from computer science. This is non-monotonic logic, right? And there's interesting application in multi-agent system. Okay, so now we're going to talk about permission. Okay, so let's think about a deadline situation, right? We are all familiar with deadlines, either as a student, right? You have to hand in your term paper, or as a researcher, right? There's a deadline for a conference that you have to meet. And very often with deadlines comes the following. So when you read the call for paper, or you hear the instruction of the lecturer, there's a following statement. You may hand in your submission in PDF or in Word. Okay, right? So, or the lecturer might say, it's allowed, you may submit your term paper either per email or bring me a paper copy. Okay, right. Now what do you conclude from that, right? It seems weird to say you may submit a PDF or a Word document, and then, but not a Word document, okay? So usually what most of us would conclude from that is actually that we're allowed to do both, right? So if I may end in my term paper or the submission in PDF or in Word, then I'm allowed to end it in PDF, and I'm allowed to end it in Word, right? I'm allowed to choose freely between the two, okay? And that's what's been called free choice permission, okay? Now, and that's what we'll talk about today. So here's free choice permission. If alpha or beta or P or Q is permitted, then alpha is permitted and beta is permitted. Okay, that's a free choice permission principle. Now, from the logical shape of it, deducting an and from an or, right? As a logician, you might quote Jan Solo and say, I have a bad feeling about this, right? This is not going to go well, right? And indeed, I can reassure you this is not a valid formula in SDL, right? So it's not true that if P or Q is permitted, then both P and Q is permitted, because remember what P or Q permitted means, it means there is an accessible state where P or Q is true. Well, it could be that it's just a P state and there is no accessible Q state, right? And then you get just one of them, but not both, right? Okay, so this is certainly not valid, right? So, but suppose you like the sort of example that I gave to you, right? So if you're allowed to hand in the submission by PDF, in PDF or in Words, then you're allowed to do both, right? Suppose you say, oh, I like it, so I will add it to SDL, right? What happened? Well, a lot of bad things, indeed, right? Or a lot of so if you add it to SDL, right, you get a lot of counterintuitive consequence. And I want just to run through a number of these. All of these are very well explained in another handbook chapter, this one by Sven Ove Hansen on permissions. Okay. So the first bad counterintuitive consequence, right? Yeah.
Canonical for any properties of canonical?
We will see it's canonical. Well, basically everything collapses if you add it to SDL, right? Because it makes, well, technically speaking, right? So if you look at the set of propositions which are necessary or obligatory, right? This set is usually upward close, so close under superset, right? But not downward close. This makes it downward close, right? But if that's the case, and tautologies are obligatory, right? If it's downward closed, then anything is obligatory, right? So that's the property you get. But we'll see it in more detail in a minute. Okay. So here's the first bad consequence, right? If you add free choice to SDL, you get that if I ought to help the poor, then I ought to help the poor and lie to my mother, okay? For whatever end that you want, okay, right? So why does it follow from SDL? Anyone sees that? Yeah? What? Yeah, exactly, right? Whoops. So O phi, right, implies, well, okay, let me just put it this way. So free choice is this. N, thank you. So that's the downside of this writing software. I cannot erase piecemeal. So if you know a better writing software on Linux for writing on slides, let me know. I'm interested. Okay, so that's free choice, right? But if you just contrapose it, what do you get? You get this, P phi and P psi implies not. Right? That's the contraposition of free choice, right? Okay. Push this negation inside, you get this. O. Right? And now you put this negation inside of this one, right? Yes, thank you. That's good. Yeah, that's even better. So now push it here. And now we're basically done, right? Why is that? Because if P or Q implies R, then P implies R, and Q implies R, right? Okay. And now you can substitute this negation for plain formula, and there you are. Okay, and you have the derivation you want. Okay. So this is one of the bad consequences. In the interest of time, I'll run a bit quickly on those, but there's a number of other ones. If something is obligatory, then anything is permitted. That's a consequence of free choice, right? Good news, right? So a lot of things are permitted. If something is, you don't even have to be obligatory. If something is permitted, then anything else is permitted, right? So again, a lot of things are permitted. That's very good. And that's actually a more interesting one, or a nicer one. It's been called by Sven Ove Anson the vegetarian free lunch example. So if I'm allowed to order vegetarian, then I'm allowed to order vegetarian and not pay for it, okay? And to derive this principle, you actually need very little, okay? So let me show you how this goes, right? So suppose I'm allowed to order vegetarian, okay? Well, we know by propositional logic that every formula can be decomposed in sort of the disjunctive normal form, right? And in particular, phi is equivalent, just in propositional logic, to phi and not psi. That's psi, right? Or phi and psi, right? That's just a classical propositional logic equivalence, right? So I can substitute that here. So if phi is permitted, then this thing is permitted. Right? But then I have a permission ranging over a disjunction, so I can apply free choice and conclude P phi and psi. Okay, right? And that's a pretty bad consequence, because the only thing you need for that is actually substitution under logically equivalence, right? All the other that I use genuine SDL validities, right? But this one is just a very, very basic valid. So you just have to be allowed to substitute this for that, and then you're done. Okay? Well, actually, the system that I'll present you to introduce free choice does have substitution. And I'm willing to fight philosophically for to convince you that this is not that bad as you might think, but we might discuss it later on, and I'll give you references to systems that do not have this consequence towards the end. Okay. Now, let's go back to the principles. Why on earth would we want free choice? Okay. Well, let's appeal to authority, at least for a start, right? So here's von Rit, right, who says not in the 51 paper, but later, he says, it seems to me that the most natural way of understanding the phrase, it is permitted that P, no circumstances being specified, is to say that P is permitted no matter what the circumstances are, that is, in all circumstances. Okay? So, under this interpretation, if I'm saying it's permitted to smoke, I'm saying every way to smoke are permitted, right? So that's what von Rit is saying here. And this is something which has been investigated in the literature, something which has been called strong permission. And I'm going to say a little bit more about this, right? So it's something that other people, like Jan Broersen, have called the open reading of permission. It says P is permitted if every execution, and here I'm talking more about ought to do, right? But you can think about ought to be as well. P is permitted if every execution of P or alpha is okay or permitted, right? Every token, right? So what I mean by okay, right? I just mean here legal, or you don't incur a sanction, you don't go to prison, right? If you do P or something like that, right? So this has much of the flavor of what I called earlier the Anderson-Kanger reduction, because you define P in terms of a deontic constant, right? Okay, here it's okay. In Anderson and Kanger, it was just the bad thing happened, right? Okay. Now, it should be clear, at least in a quasi-formal way, that if you interpret permission this way, right? So for all possible circumstances, if it's the circumstances where A is done or A is executed, then you're in okay circumstances, right? Free choices follow, right? But from that, you need just one particular example or one particular property, what I'll call additivity. So if you execute an A action, then you execute an A or B action, right? Okay. Or if the program alpha is executed, then the program alpha or beta is executed. And if you're, for example, familiar with PDL, right, and you take the or here as non-deterministic choice, right, that's how it works, right? So this is certainly valid. In fact, this is a biconditional. You have alpha or beta if and only if alpha or beta, right, in PDL. Okay. Now you can see how this will go, right? So suppose phi or psi is permitted. Right? Okay. Well, what does it mean, right? It means that for all objects, for all action, right? If it's an alpha or, well, phi or psi action, then it's an okay action, right? Okay. But now if I have additivity, right? That is, if something is an alpha action and it's an alpha or beta, right? I can use transitivity of material implication just to conclude that for all x, if x is an alpha, then x is okay. But that's just the definition of x being permitted according to the open reading, right? So we concluded that alpha or, sorry, I switched between phi's and alphas, so there should be a phi here. I just concluded that phi is permitted. Okay, right? So the open reading gives you free choice, right? Okay. And that might be a reason why you want to do it, but if you want to do it, and you don't want all the bad consequences, you have to do something else. Now I'll show you briefly how to do something else, okay? And this way to do it, one way to do it is to move to something that's called non-normal modal logic. Okay. Now this is a whole field of study in itself. The classical reference of that is Brian Chellas, okay? Textbook on modal logic where he treats non-normal system. But I guess the most up-to-date reference is Eric Packett's course on neighborhood semantic for modal logic, right? So you can go to his website, the address is here. It's a lot of course note and slides, which are much more up-to-date than Chellas. I mean, Chellas by now is what, 34 years old. So I think Eric must be, he's a bit older than 34, but not much. So you should really, if you want to look at what's neighborhood semantic now, you should look at Eric's work, okay? So a non-normal model system is just a system which does not validate K, the K axiom, or necessitation, okay? So it's a system which is weaker than K, okay? And the standard semantic for that is what's called neighborhood semantics. So to understand what neighborhood semantics is, you just have to think a bit of what Kripke semantic is. So you remember I interpreted the deontic models, right, O phi, in standard deontic logic as phi is true in all the accessible state. Okay? Now suppose I'm at a given state. I can make a list of all the things that are obligatory, right? All the phi such that phi is true. O phi is true at that state, right? That's a list, okay? Right, so all the phis that are true in all the accessible state. Now, this list will have a number of properties, okay? And you can deduce or already think of some properties of this list by some of the theorem of SDLs we've seen. For example, we saw that in SDL, obligation distributes over conjunction, right? So if phi is obligatory and psi is obligatory, then the conjunction is obligatory and vice versa, okay? Well, the first direction is to say that this list is going to be closed under intersection or under conjunction, right? So if phi is in the list and psi is in the list, then phi and psi is in the list, okay? Necessitation tells you that tautologies or the whole set of state is always going to be in the list, okay? Well, neighborhood frames take this idea of list and abstracts away from this relation, right? So each state in the model, instead of being connected to other states, just get a list of propositions assigned to itself, which tells you what is obligatory at that state, right? So in a picture, right? So suppose I have my big set of state, W, and I'm looking at W here, right? Each state W is going to be assigned not a set of accessible world, but a set of proposition. Maybe this one, maybe that one, right? And maybe this one. Okay? So this little neighborhood model, right, as at W, there's three things that are obligatory. The proposition which is expressed by this set, by that set, and by the third set, okay? So what I mean by propositions here are sets of possible worlds, okay? And this is going to be defined by this n, which is what's called a neighborhood function, right? That is, it's a function from state to sets of states. So each state gets assigned a list, right? Okay. And a neighborhood model is just like we had before, a neighborhood frame, except that states get assigned propositions that are true at that state. What?
Arbitrary subsets.
Yeah, arbitrary subsets.
It's not that there is some proposition as this.
No. So it's arbitrary, right? The list could be empty. The empty set could be in the list, right? These are two different things in neighborhood semantics, right? A lot of things, right? Whatever you might want to have, okay? And in particular, this list will not necessarily have the property that it would have if it would come from a Kripke semantic. And that's the important thing, okay? Now, truth in neighborhood semantic is very simple, right? It just says that all phi is true if and only if the interpretation of phi or the truth set of phi is in the neighborhood. So I want to know whether phi is true. All phi is true at a state. I look at the list. If phi is there, phi is obligatory. Okay, that's just what neighborhood semantics gives you. So it's a very simple truth definition. So to go back to our little example, if I have W and it's get assigned, let's say these two, right? And I want to know whether O phi is true here, right? Well, what do? I check if one of those circles is exactly the truth set of phi. So if this is exactly the truth set of phi here, then indeed phi is obligatory, right? This is just what I do. Right? Okay. Now, it's important this is exactly, right? So not containing, right? Okay. So one way to rephrase that definition, right, is the following, right? So O phi is true if and only if there is an x in the neighborhood of W, and for all W prime in X, well, we have for all W prime is in X if and only if W prime make phi true, right? Okay, and that's a crucial thing, right? Because so it's really an if and only if here, right? And if you look at this definition, it might remind you of something if you're familiar with topological semantics from modal logic, right? This has also this exists for all flavor, and indeed, topological models are a special case of neighborhood models. Good. So, indeed, once you have that, right, then you lose some of the classical SDL validity. For example, closure under intersection need not to be the case, right? Okay. So I just have to take a model where phi is in the list, psi is in the list, but phi and psi, the intersection, is not in the list, right? And then I have a counterexample to this, right? But someone asked me earlier, what is free choice canonical for, right? Well, this principle here is canonical in neighborhood model for the neighborhood function to be closed under intersection, right? Just reading off this principle. So if phi is in the list and psi is in the list, then the intersection, that is a conjunction of phi and psi, is also in the list.
Just one question.
Yeah.
So we had the problem that we wanted to attack the feature, then we were getting P bottom.
Yeah.
Which is not doing any relational crypto frame.
Yeah, exactly.
So we will move to this neighborhood semantics.
Yeah.
Now we started putting properties of neighborhood semantics to include our axioms like.
Exactly. Exactly. Right. That's what we're going. Right. Right. But one thing I haven't told you, right, is how to interpret P in there. Right. I haven't told you that yet. Right. So I just talked about O's. Right. And I won't tell you yet. Right. So give me a couple of minutes and I'll tell you 2 ways to interpret P in this system. But indeed, this is precisely the game we're playing now. We're having an arbitrary neighborhood function, and we're now going to see what kind of property do we want and what kind of property do we have. Because it's a very weak semantic, that is, it doesn't validate much, but it does validate some things, and we'll see which one. Okay? Good. So here it is. If you don't make any assumption on the neighborhood function, then there's actually very little. So the logic that corresponds to neighborhood frames, arbitrary neighborhood frames, just contains propositional tautology and is closed under one single rule, namely extensionality. Okay? So if phi and psi are logically equivalent, then you have O phi if and only if you have O phi. They're both obligatory or not obligatory at the same time. Okay? And if you think of it semantically, it makes a lot of sense, right? Remember, O phi means the interpretation of phi is in the list. Well, if phi and psi are logically equivalent, then the interpretation of phi is just the same set as the interpretation of psi. So the interpretation of psi is also in the list, so we have O psi, right? And vice versa. Okay. And this is modus ponens, right? It's just propositional logic. And that's it. Right? So if you have an arbitrary neighborhood frame, that's all you have, right? Okay, so if you want more, you have to add them manually, right? So on top of what there is. So it's a very weak logic. The other thing it allows you to do is substitute things that are logically equivalent within the scope of the O. Yeah?
You wanted the seriality problem.
Yeah.
What does that do?
Very good. So seriality here, well, okay, now let me start with the axiom. So the axiom we had earlier was O phi implies P phi, right? Okay. Now, in neighborhood semantics, there's 2 senses of seriality, right? So you might think of the equivalent of, or the counterpart of seriality being there is something in the neighborhood, right? Okay. So if the neighborhood is not empty, right? There is something which is obligatory, right? Okay. That would be sort of the direct counterpart, but this won't give you that, right? Okay. And actually, that the neighborhood is empty or not is not something you can express, actually, right? Okay, you can say that specific things are there, for example, tautologies, but you cannot say there is something, whatever, right? Okay. Now, if you impose that, well, now I guess I cannot escape it anymore. I have to tell you what P means in neighborhood semantics. Okay. Now, let's go back to the truth condition, right? So, all phi means phi is in the list, right? But if you unpack it, it means there is a set in the list which is exactly the interpretation of phi, right? Okay. Now, if you take phi, p phi to be the dual again, right? And you push that definition through, right? But it gets a bit complicated. But basically what you do to get the dual is to say p phi means for everything in the set, it's consistent with phi, right? Okay, that everything in the list, right? So all of your obligation are phi consistent. There is a phi state in everything in the list, right? That's usually the way it's done, right? Okay. But why I push the suspense so long before telling you that, right, is because you remember this one bad consequence that we had about free choice, namely the vegetarian free lunch, right? If I've, so we had a number of them, right, of bad consequences, and a lot of them were using this duality here between O phi and O, well, not O naught and P, right, okay. Now, in neighborhood semantics, actually, you are free to interpret P whichever way you want. You can give it this dual notion, but you can also interpret it independently, right? And if you do that, then you avoid a lot of the bad consequences of free choice, right? And this is what, well, I won't have time to present you this, but this is what I've been doing with a couple of colleagues in the past years. So you have much freedom in neighborhood semantics and how you define P, right? And it doesn't have to be dual. And I'll say a couple of reasons why in a minute about why you want to do this. Okay. So now I just want to finish by pointing out a couple of things. So how is neighborhood semantics related to Kripke semantics, right? Well, actually you can show that K, which is the logic of all Kripke frames, corresponds precisely to a subclass of all neighborhood frames, namely those that are augmented. And what is an augmented neighborhood frame? It's a neighborhood frame which is closed under both arbitrary union and arbitrary intersection. Okay? Right? So it's, and now you have to tell me if you know your topology better than I do. Is it an Alexandrov topology? Yes. Good. Good. Okay, so that's what it is, right? So K is exactly the logic of neighborhood frames which have these properties. They're closed under arbitrary union and arbitrary intersection, not only finite intersection, okay? Or in other words, they contain their core. If you look at the intersection of all the sets, it could be the empty sets, but that's okay. It has to be in the neighborhood as well, okay? And that's, and in fact, there's a representation theorem that goes with this result. For any augmented neighborhood frame, you can devise a Kripke model. You take the core and you make it the set of accessible world, okay? And if you have a Kripke model, you can make it a neighborhood frame. You just take the list, right? Okay, and this will have all the properties that you have there, right? Okay, so there is a nice correspondence between neighborhood frame and Kripke frame. And if you're interested in that, please go to Eric's note. This is something which is not in Brian Cella's book, but this is definitely in Eric's notes on modal logic, Eric Packett. Okay. I will not tell you this. So I wanted to tell you a nice story about something that I wrote with a couple of colleagues, but I'll drop that. I just want to go back to free choice. So one thing you might want to do if you're interested in incorporating free choice in a way that doesn't create disaster is two things. First of all, I think it's plausible to think that O and P are not necessarily dual. Okay? And why is that? Well, look again at what it means when you interpret P as dual. It means as soon as something is not forbidden, then it's permitted. Okay? Right? This is precisely what it does, right? It defines permission as the absence of prohibition. But you might want to think that in some case, the law or morality is just silent on some issue. doesn't say that it's obligatory, but it doesn't say that it's permitted either, right? Again, an internet-based example, you might want to think about file sharing. When I started to use the internet, so mid-90s, right? We were all sharing files. Nobody does that anymore, of course. But at that time, there was just no regulation regarding file sharing, right? No copyright regulation, whether it was permitted. I mean, right now it's forbidden in many countries, right? But at the time, there was just no regulation. So it was not the case. It was the case that sharing was not forbidden, right? But it was not the case that it was explicitly permitted either, right? So you might, for that reason, want, and if you want to allow a system that does that, you need to decouple these two and have P as a primitive operator. And if you do that, then you're free to interpret permissions in neighborhood terms. And then to finally answer your question, this will correspond to your neighborhood being closed under subset, right? So if phi is in the if P is if phi is in the list and psi implies phi, then psi is also in the list, right? This is basically what this will do. Okay. Now you get, because of that, if you're a neighborhood frame, the vegetarian free lunch case, right? So, and you might not be happy with that, but then again, as I said, I'm willing to go into a philosophical argument with you as to why it's not that bad, right? But if you are really, really unhappy about this and you skip all of this and you go read Hans Kamp, this is what you do, right? So if you're interested in free choice permission, then there was an early paper by Hans Kamp who devised a system which gives you free choice without giving you vegetarian free lunch type of counterexample. But it does this in a very pessimistic world where the default assumption is that everything is forbidden unless it's explicitly permitted, right? So that's how things work in this system, right? But that's a very nice solution, and I just want to point you two things to finish, namely that free choice has attracted a lot of interest in linguistics, actually, right? And why is that? Because one way to think about the free choice phenomena is to think about it as a pragmatic thing, right? So you remember how I introduced it, right? I said, you read the call for paper, and it says, you may end in your paper in PDF or in Word. Right? But I said it would be very weird then to have as a next sentence, right? But please don't do it in Word. Although you might think that, right? Please do it in PDF. But it seems there's something weird about that, that our utterance of the permission is unsuccessful, is not as informative as it should be if we cancel it right away by negating one of the disjunct, right? And this is precisely the type of pragmatic implicature, right? You've talked about implicature earlier. So this is precisely the kind of pragmatic phenomena that has been used to account for free choice. So there's Karin Schutz, who's in Amsterdam, who wrote a very nice paper about it, or Asher and Bovenak, also two synthèse papers that talk about free choice. And they both use resources for formal pragmatic theories to account for the free choice paradox, which is a completely different ballgame than what I've been doing now, but makes a lot of sense given what I just say, that when we make free choice inference, it seems to make it on pragmatic ground, right? So when I say, if I tell you, you may end it as PDF or Word, but please don't do it as Word, right? What you reply to me is, but why did you say that in the first place, right? Why didn't you just say, well, just do it in PDF, right? And that's typically the sign of pragmatic inference, that it's in the background, and if I'm giving you only that much information, right? If I'm informative as possible, that's a Gratian maxim, then I should be allowed to do both, right? But again, that's pragmatic or linguistics, where the ontic logic has been flourishing, and that's probably one of the reasons for that. And I'll leave you with this. So thanks so much, and see you tomorrow.